Hello everyone, this is Mohsen from the Ozen Engineering team. This is the second part of the video about using Flownex software for modeling power plant. In the first part, I just used the model available from Flownex team for the combined cycle power plant, which is a combination of gas turbine and steam turbine together, and so we have uh, more efficiency and uh, better overall power generation for the power plant. In part one, I already showed you how to use this model or how to run it and what are the main parts and main systems of this of the power plant cycle. In this part, I just want to show you how to change the mass flow rate of the fuel that used in the cycle, and also how we can consider different weather conditions, ambient conditions for the power plant, and evaluate the effect of these two on the production of the power cycle. Please watch this video. Okay, in the next part of this video, I want to just show you how to change the fuel mass flow rate uh, in for the power plant. Basically, we want to see that there is effect on the efficiency and on the output, total output power. This is the model that I have. I just again initialize that. Uh, let's run it for a steady state condition, and again we see non-zero value for uh, energy source. We don't want to have any magnitude for the energy source. It means that, so I'm again run the designer, and I will show you then how to change this mass flow rate for the for this fuel, for which is natural gas here. Now this is designer running. Okay, almost zero, so there is no need for the input of the energy source for this two-phase tank, which is a boiler drum. Now let's work on the mass flow rate of the natural gas. We go here to the configuration, and we can define some actions that it is in base of time. For example, we can say that from when start what changing what parameters. Here we have some set of value for the uh, uh, pressure and the Q value there for the boiler. If you come here, and you can see that from time 0.2 second, for example, we can see that this one, it is for the pressure, okay, and this one for the here for quality. So this one is the one that I want to see, that fuel mass source. It is said that after half a second, okay, I start to change this fuel inlet. This is a pressure, this is the boundary condition, this source for the mass. Initially it is set at 4, and we use this value for a steady state condition. We want to change it in a way that, okay, that Now you can see it is a function of the time. It is a constant which is 4, and after that it is like a linear changing in the magnitude in terms of time for the mass flow rate. But I don't want to go beyond 5 kilogram per second, not more than 5 kilogram per second. So this is the action that I have. So when I back to the model, and if when I start this transient simulation, you will see that this value start changing after half a second. We didn't have this before when I ran a transient simulation. Let's see. Okay, time is 0 0.4. Now we should see changes into the magnitude of the mass flow rate. Yeah, it's capped at 5 kilogram per second. The air intake is also changing, the magnitude of the air coming in. Okay, you see the change in the output power for the gas turbine. Okay, and also the steam turbine. Let's see how much we will see. So the magnitudes that right now for the total value, it is of the power, it is 83.8 megawatts, and the overall efficiency for this cycle or for this condition, it is 30.6%. Let's see. Now it is 6 seconds. We see that. So again, you see that the power for the gas station is almost constant. Okay, 44.3 something, 44.3. But the magnitudes for the steam turbine is changing. Let's see. 18 megawatts. You can see that in the boiler system, which is heat recovery for steam generation, we see a little bit changes in the temperatures. It used to be 700 somethings, 600 somethings degrees Celsius, and this is 410, 20 somethings. Now you can see that for sure we have higher temperature because of the higher inputs for the fuel, and after combustion it will input gives more power to the turbine, and turbine production for sure will increase. Let's see, what time is it? 18 seconds. We're getting close to the end for this transient simulation. So yeah, you see that 19.8, almost done. We're done. Okay, we're done. Again, you see that constant output power almost for the gas turbine, but the steam turbine, the output for the steam turbine, this power increasing. Okay, is about 19.67 somethings. Okay, and if we check that, yeah, 19.7. So we are seeing that increase in the efficiency and the total power due to the increase in the mass flow rate, and this is the boundary condition that for in this one with the action we change the magnitudes of this mass source from 4 up to 5 kilogram per second for this boundary condition. So as you can see, we have zero input for the zero magnitude for the heat source for the ramp for boiler, which is good. So increasing in the efficiency and total output power when we have more fuel gas. Let's see that if we increase it more from 5 kilogram now to 6 kilogram, what's happened. So I'll go and change the action here and see what's happened. Okay, we go back to the initial condition, 4 kilogram per second for the mass flow rate of the fuel. Go to configuration, action setup. This is for mass flow rate. I will change this maximum to 6. You can see that I change it to 6, so it means that the mass flow rate starts at 4 kilogram per second, and after half a second it will start increasing up to 6 kilogram per second. Okay, so I adjusted that action. Go for a steady state condition. Again, check the boiler drum and negative energy source. Go for the designer, run the designer to change the pressure here. As you can see, pressure of the drum, that you see that you can see that here it is changing gradually, and then we can back to the energy source here and see that half is working. So let's see. Yeah, I found the solution though, so the solution converged, and if now you can check it, okay, you can see that almost zero, which is good for the energy source. Now we can go and run transient analysis. Okay, 0.4, 0.5 second, and you can see that the mass flow rate of the gas start increasing. 5, 5.2, 5.4, and 6. So it does not go above 6 kilogram per second. And meantime, you can check the exhaust temperature. It is much more than before, as you can see. Also here for the temperatures in the gas line and the exhaust line to the ambient, now it is 500 somethings that you can see. Okay, the output power, it is 58.1 for the gas turbine, and for the steam it is 18.1, and see, so it is 8 second. The output power for steam turbine is increasing, going up. Let's wait until 20 seconds that it will finish the transient analysis. Now we are above 19.5 for the power compared to 17 somethings that we had before. Maybe we go beyond 20 megawatts from the steam turbine. Yeah, but the power generation for the gas turbine is constant because we don't see any changes here anymore. for the intake air and for the natural gas input. Okay, we almost at the end. Let's see what is the time. It is still increasing. 19.4 second, 19.6, 0.8, and yeah, I almost yeah, 20. Okay, we're done. 21.9 for power megawatt for the power generation of the steam turbine, and the total output power it is 97.6, but the overall efficiency dropped from 30.6 to now 30.1. And so you can see that the output power of each of these gas and each of these turbines depends to the for sure the uh, mass flow rate of the fuel. But one thing is that we have to also note that the other parameters here we have to look at that. For example, here the exhaust temperature it is above 1000. It is 1200, more than 1200 second. Maybe this is beyond the temperature limit for the pipelines on some insulation, which is not good. Okay, and we need much more power. It is for the uh, water circuit system that we have, and the temperature exhaust gas temperature now it is above 500. So these are some things that we need to also consider to know that. But here I just show you that by new action that I set it up here. Okay, uh, here, okay, that I set it up here. Instead of cap it at 5, I cap it at 6 kilogram per second, and we can now see the effect of the mass flow rate of the fuel gas on the performance of the cycle of the power plant. Now let's check the weather conditions and see that how these different weather conditions could affect the performance of the power generation cycle. Okay, I haven't talked so far about this one, okay, that it is for air psychometry. If you double, you can see that the inputs, okay, are site elevation, atmospheric temperature, and relative humidity. And this icon it is for the raining day. It means that because of the specifically relative humidity that you can see that we expected to see a kind of weather for raining days. Let's double click on that. Okay, it is do the calculation from the psychometry charts that we have. You can see that here from these inputs we can have some information about atmospheric data like ambient pressure, density, relative humidity, and dew point temperatures, and also results on the air composition based on the mass fraction or mole fractions that here. So I decrease the relative humidity and increase a little bit elevation and also the temperature. So we have new information from the for the atmospheric data. Let's see what is the effect of these changes on the performance of uh, the power plant. And this is the script, okay, that you can see that it takes the information from the psychometry chart and do the calculation for the based on the formulations that we have for the parameters here as a result. And you can see that what are the inputs, what are the outputs here. So go back to the model. These are the new information for the weather conditions. A little bit higher elevation and also lower relative humidity. And see what is the effect of this on the performance of the power plant. First run the steady state condition, then run the designer to have zero energy source for the boiler. By changing the pressure of the drum, boiler drum. Okay, almost zero, which is good. Now for this new information from weather condition, let's run the transient analysis. So the gas flow rate is kept at as is, as 4 kilogram per second. You can see that. Now we can see the changing in the way that the the power outlet from the gas turbine changed. The power output for the graph for the gas turbine, it is different from before. I will back when the solution done. About 10 seconds pass. We need to have it run until 20 seconds. The solution is done. Okay, the power generation for the estimate is 17.3. It used to be 17.5 in the previous weather conditions, and the power generation of the gas turbine now it is 24.2. It is a little bit better. It used to be 23.9. So the total power generation, it used to be 63.4 in the raining weather conditions. Now it is 63.7, and a little bit increase in the overall efficiency. It used to be 28.8, now it is 28.9 percentage. So we see that the effect of weather on the performance of the of the uh, of the power plant. Let's do more changes to the weather condition and see what is the effect for that. So let's change this to the elevation from original amount to 1000, so it is like really going up above the sea level. This one, change it to 18 and lower lower relative humidity, so it is like a almost dry condition. Depends to the weather, where and location and the other atmospheric conditions. uh, we also here need to change the configuration and change the limit minimum maximum to 2000 up to 30,000 for the boiler to get an answer or converge solution for the boiler with zero energy source. Okay, I find these values by changing these values, and see that for this value of the limits for the pressure of the ROM boiler, the ROM, we can have the answer. Let's run first. Go. So this is new condition, new weather condition. Let's go for weather. For the steady state condition, steady state, I already run it. Run designer. Okay. So let's see, almost zero, which is good. That we have. And now let's run transient. Go for transient running. Same mass flow rate for the gas, natural gas. I will back when the solution done. The solution is done. 20 seconds. As you can see that the steam generation produces 18.9 megawatt, which is larger than before, and the gas turbine produces 30.6, which is also this one more than before. So the total power output is 70.1, which is more than the previous weather conditions that we have, and we have much higher overall efficiency. So this is very good. You can exactly see the effect of the weather on the performance of the power plant cycle. I was running this model for this different weather condition and changing the mass flow rate by using the actions that I already showed you in this video. This is this is the results for that. Okay, this table summarizes what we have. We have here the three different weather conditions, and here you can see the different mass flow rate, kilogram per second, efficiency, the powers for the turbines, and the total power. So you can see that when we changing the weather conditions for each specific mass flow rate, for example, mass flow rate of the fuel, for example, 4 kilogram per second, the efficiency increases, okay, from 28.8 to 28.9 to 31.9%, and same for the output power. And this is also the same scenario we are seeing that when we check it for 5 kilogram per second and 6 kilogram per second. For example, for 5 kilogram per second, the efficiency for this weather condition, it is 30.6%, increases to 30.9, and then jump it to 31.9%, which is good. And for total power, from 83.8 jump it to 84.6 and go up to 87.4. So also we see the summary of the effect of the changing the mass flow rates for different weather condition. We see same trend that for the rainy days, like raining days, okay, for 4, 5, and 6 kilogram per second, efficiency goes up, but from 28 to 30.6, but for the 6 kilogram per second, it drops. And we see same scenario here for the other weather conditions. So in this video I showed you that how to use the available model for power plant, for combined cycle of power plant from Flownex, how to work with that and have to change the mass flow rate and see the effects on the performance of the power plant, and also have to change the weather conditions and see the effects on the efficiency and the total power plant. Hopefully you enjoyed this video. Thank you for watching.